Welcome to my online course in linear algebra for undergraduate mathematics. Today's topic of discussion is linear transformation. If U and P are two vector space over the same field F, then the mapping F from U to V is said to be linear transformation if f of alpha x plus beta y is equal to alpha fx plus beta fy, where xy belongs to vector space U and alpha beta belongs to F. Further, if F is 1, 1 and on 2, then F is said to be isomorphism from U to V. It is written as U isomorphic to V. A linear transformation from the vector space V to V itself is called linear operator, whereas a linear transformation V to F, the field, is called linear functional. Next is example. First, consider the function f from R3 to R defined by f of a1, a2, a3 is equal to a1, a2, so that f is a linear transformation. For that, we consider two elements a equal to a1, a2, a3 and b equal to b1, b2, b3 in R3 and alpha, beta, b2 scalars in R. Then alpha a plus beta b is equal to alpha of this element a1, a2, a3 plus beta of this element b1, b2, b3. In next step, bring this alpha inside the bracket. It will become alpha a1, alpha a2, alpha a3 plus bring beta inside this bracket. We will get beta b1, beta b2, beta b3. Then add this pairwise, we will get alpha a1 plus beta b1, alpha a2 plus beta b2, alpha a3 plus beta b3. In the next step, you should take f image of this element and f image of this element. The next, using the definition of this mapping, we will get this one. Here it is f image of left hand side element and f image of the right hand side element. Then using the definition of the mapping, we will get first two elements, that is alpha a1 plus beta b1, alpha a2 plus beta b2. Then separate alpha with alpha and beta with beta. We will get this one, that is alpha a1, alpha a2 plus beta b1, beta b2. In next step, take alpha common. That will give you alpha common from this first term. We will get alpha a1, a2, and from the second term, take beta common. It will be beta b1, b2. Then this is equal to alpha by definition of the mapping. This is f of a next plus beta f of b. Therefore, f is linear transformation. Next, let V and F be a vector space of n tuples of the element from the field F, and F from Vn to F defined by f of a1, a2 up to an is equal to a1x1 plus a2x2 plus dot 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 an xn, where x1, x2 dot 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 xn belongs to F, a1, a2 dot 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 an belongs to Vn(f). So that f is a linear functional from Vn(f) to f. We consider two elements a equal to a1, a2 up to an and b equal to b1, b2 up to an be two elements of Vn(f), where ai's and bi's belong to the field f. For any two scalar alpha, beta, their linear combination alpha a plus beta b is equal to alpha a1, a2 dot 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 an plus beta b1, b2 dot 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 bn. In the next step, bring this alpha inside by the property of scalar multiplication in Vn. This will give you alpha a1, alpha a2 dot 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 alpha an beta B1 beta B2 dot beta Bn. In next step, add them pairwise, we will get alpha A1 plus beta B1, alpha A2 plus beta B2 dot alpha An plus beta Bn. Then take F image in left hand side and right hand side. We will get this step, that is f of alpha A plus beta B is equal to f of alpha A1 plus beta B1 alpha A2 plus beta B2 dot alpha An plus beta Bn. Then using the definition of the mapping given here, f of a1 a2 up to an is equal to a1 x1 plus an xn. Using these definitions, we will get this one: first element into x1, second element into x2 up to nth element into xn. Then separate alpha terms with, write alpha terms with alpha terms and beta terms with beta terms. We will get this one. Take alpha common, that is alpha into a1 x1 plus an xn. Then in the second term you will get plus beta b1 x1 bn xn. Then again, using the definition of mapping, we will get alpha f of a1 a2 an plus beta f of b1 b2 bn. This is your alpha f of a plus beta f of b. Hence, f is a linear functional. Next is properties of linear transformation. If f from UF to VF is a linear transformation, then f of 0 is equal to 0 dex. That means f image of the 0 in U is equal to 0 dex of P. And second, f of minus U is equal to minus f of U. Third property, f of U minus B is equal to f of U minus f of P. Fourth property, f of alpha 1 u1 plus alpha n un is equal to alpha 1 f of u1 plus alpha 2 f of u2 plus alpha n f of un, where UP belongs to the vector space U and u1 u2 un belongs to U, and alpha 1 alpha 2 alpha n are scalars in F. Proof: let 0 and 0 dex are zeros of the vector space U and P respectively, and consider U belongs to small u belongs to capital U, and then f of u, f of small u belongs to B. Therefore, f of u plus 0, since u belongs to capital U and 0 is the additive identity of u, so u plus 0 is equal to u. It does not create any change. So f of u can be written as f of u plus 0. Since f is linear transformation, this can be written as f of u plus f of 0. This f of u plus 0 is my u. So this is your f of u plus, I am having 0 dex of B, as f of u is an element of B. So adding 0 dex with that element does not create any change, as B is a vector space, and right hand side will remain as it is. Then using the left cancellation law in V plus, we can cancel out this f of u from both the side, and this equation becomes now 0 dex is equal to f of 0. Number 2, we can write f of u plus minus u by, since f is a linear transformation, so I can write this f of u plus f of minus u. In the left hand side, u plus minus u is my 0, so f of 0, as u and u belongs to u, that is capital U. Capital U is a vector space, so addition of a element with its additive identity is 0, so this element is 0. that is f of 0 is equal to f of u plus f of minus u. By first property, f of 0 is my 0 text. This is equal to f of u plus f of minus u. Therefore, f of minus u is equal to minus of f of u. Third property, f of u minus p is equal to f of u plus minus p. Since f is a linear transformation, so this can be written as f of u plus f of minus p. By using the second property, I can write f of u minus f of p. Now we are going to prove the fourth property. This property, we will prove this property by induction. That is, we will show that this property holds for n equal to 1. That is, when I take one vector, this property holds. Then I assume that this property holds for n minus 1. Then I will show that this property is holds for all n. Hence, by mathematical induction, this property holds for any natural number. Now proof. For n is n equal to 1, take only one vector. That is, we have f of alpha 1 u1. By using the definition of linear transformation, I will get alpha 1 u1. So this result holds if n is equal to 1. Next, we suppose that result holds good for n minus 1, that is f of alpha 1 u1 plus dot 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 alpha n minus 1 u n minus 1 is equal to alpha 1 f of u1 plus dot 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 alpha, this is n minus 1, f of u n minus 1. Put this equation 1. Now we shall show that result hold for any n. Take f of alpha 1 u1 plus alpha 2 u2 plus dot 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 alpha n un. This can be written as f of alpha 1 u1 up to alpha n minus 1 un minus 1 plus alpha n un. Since f is a linear transformation, I can write in place of this, I can write this one. That is f of this element plus f of this element. In next step, use equation 1 and write this one. That is, instead in place of this, I will write right hand side of this equation 1. And this equation ultimately reduces to this equation. That is, this is finally equal to this one. Hence, the result is true for n. By mathematical induction, the result is true for any natural number. Home assignment. These are your home assignment. Solve this. In case of any doubt, any difficulty, you can ask me. Remaining will be in the next lecture. With that, I would like to conclude. Thank you.